We all remember that lesson from science class, right? The Earth's surface is this giant jigsaw puzzle of tectonic plates, and all the action, the earthquakes, the volcanoes, it all happens where those puzzle pieces grind against each other. It's a nice, neat set of rules. But what happens when the Earth decides to break them?
So, here it is. This is the classic model, the rule book we all learned. You can see the major plate boundaries all mapped out. See that really dense band of activity all around the Pacific Ocean? That's the famous Ring of Fire, and it's a perfect example of this rule in action. The thinking goes, this is where pretty much all of the planet's tectonic drama is supposed to be. Simple, right?
But then, the Earth just loves to throw us a curveball. Take a look at this map now. We've got Hawaii, this chain of massive volcanoes just popping up in the middle of the Pacific Plate. Then there's the Yellowstone supervolcano, sitting in Wyoming, thousands of miles from any coast. And maybe the strangest of all, the New Madrid seismic zone, the source of some of the biggest earthquakes in U.S. history, smack dab in the middle of the country. These spots are nowhere near a plate boundary. They are the ultimate geological rule breakers.
And that, right there, is the central question we're going to tackle. How is any of this possible? How can some of the most supposedly stable parts of our planet be home to such incredibly powerful geological forces? Well, it turns out that simple rulebook doesn't even come close to telling the whole story.
Okay, so let's get into it and investigate these tectonic rule breakers. How do they actually work? We're going to break this down into two main parts. First, we'll talk about the shaking, the unexpected earthquakes. And then we'll talk about the fire, those mysterious volcanoes. Let's start with the quakes. To really understand the shaking, we have to look deep into the past. We have to think of the planet's crust not as some perfect solid shield, but as something with a very long and sometimes pretty violent history.
So, what is an intraplate earthquake? Well, it's what happens when stress builds up along an ancient pre-existing fault line deep inside a plate. The best way to think about it is like an old crack in the pavement. The pavement looks totally solid, but that weakness, it's still there, just underneath the surface. Tectonic plates are absolutely riddled with these ancient scars from geological events that happened hundreds of millions of years ago.
So how does an old, quiet fault just suddenly wake up? It's pretty much a chain reaction. First, you have the constant pushing and pulling way out at the plate boundaries. That sends stress rippling across the entire plate, even though it feels solid. Then, that stress naturally finds and zeroes in on an old weak spot, that ancient scar. After years or sometimes even centuries, the pressure finally gets to be too much, it overcomes the fault's strength, and bam! It suddenly slips. And the result? All of that pent-up energy is released in a massive earthquake, sometimes thousands of miles from where that stress originally started.
Now, while these ancient scars are the main culprit, there's another kind of bizarre reason for these quakes, something called isostatic adjustment. I want you to just picture the Earth's crust flexing under the unbelievable weight of 2-mile-thick ice sheets during the last ice age. I mean, the weight is just staggering. When all that ice finally melted, the crust started to slowly rebound, and it is still rebounding today. That slow, massive upward movement can be just enough to jolt these old faults, triggering quakes as the Earth still kind of sighs in relief from a burden it got rid of 10,000 years ago.
Okay, so ancient scars explain the shaking. Got it. But what about the massive volcanoes? For that answer, we need to look even deeper, way down into the Earth's mantle, for a totally different kind of rule breaker.
The answer is something called a mantle plume. Honestly, the best way to visualize this is as a colossal blowtorch rising from deep within the Earth, maybe even from the very edge of the core itself. It's this incredibly hot column of buoyant rock that literally punches its way upward, melting the solid crust from below and creating a massive chamber of magma.
And this is what we call the hotspot effect. Now, the really crucial thing to get here is that the mantle plume, this deep Earth blowtorch, is pretty much stationary. It stays in one place. But the tectonic plate on the surface, it's constantly slowly drifting over the top of it. Imagine you move a piece of paper over a lit candle. You'd get a whole series of scorch marks. Well, on Earth, those scorch marks, they're volcanoes.
The Hawaiian Islands are the absolute perfect real-world proof of this process in action. Think of that island chain like a conveyor belt. As the Pacific Plate drifts steadily to the northwest, it carries older volcanoes away from that hotspot, and they go dormant and start to erode. Meanwhile, a brand new volcano is being born directly over that stationary plume. And that creates the beautiful, linear chain of islands that we see today. It's like a geological breadcrumb trail left behind by the moving plate.
But here's a twist. Not all hotspots are created equal. Out in the ocean, like in Hawaii, the magma that's produced is basaltic and really runny, which leads to those gentle, flowing eruptions we're all familiar with. But when a hotspot sits under a really thick continental plate, like it does at Yellowstone, the magma gets all mixed up with the complex crust. It becomes super rich in silica, which makes it thick, sticky, and amazing at trapping huge amounts of gas. And that can lead to some unbelievably explosive eruptions.
So we've got these two very different mechanisms, right? We have ancient faults that are reactivating, and we have these deep mantle blowtorches. Both of them are completely breaking the simple rules of plate tectonics. And understanding them isn't just some fun academic exercise, it has huge real-world implications.
So what's the ultimate takeaway here? Well, it's that those simple rules we learned in school, they aren't wrong, they're just the first chapter. The real story is that our planet is so much more complex. It's layered with history, with ancient scars that can just reopen, and it's powered by this hidden engine deep in the mantle. And what that really means is that nowhere on Earth is truly geologically quiet. Understanding these rule breakers isn't just a fun science puzzle, it is the absolute key to preparing for the unexpected, no matter how safe a place might seem.
So we've started to uncover the secrets behind these geological rule breakers, from these ancient faults to the deep earth blowtorches. But it really leaves us with one final, kind of awe-inspiring question. Our planet's surface tells one story, but what other secrets is the deep earth still keeping from us?